Next, let's look at the transformer feed-forward layer. After attention mixes information across tokens, this layer processes each token independently with the same small neural network. It typically expands the hidden dimension, applies a nonlinearity, then projects back down. Even though it's simple, it adds a huge amount of model capacity and compute. So, understanding how it works is important both for architecture fundamentals and for real-world LLM engineering interviews. Here's the roadmap for this section. We'll start with architecture fundamentals, focusing on where the feed-forward network sits inside a transformer layer. Then we'll cover what actually gets trained, including weights, biases, and how the FFN complements attention. After that, we'll look at the key-value memory interpretation, then the system side like memory cost, chunking, and training stability, and we'll close with portfolio and interview strategies. In each encoder layer of the original transformer, there are two main sublayers. First comes multi-head self-attention, and second comes the position-wise feed-forward network, or FFN. Both are wrapped with residual connections and layer normalization. The key point here is that the FFN is not just a supporting detail. It is a core trainable part of every transformer layer and one of the main places where the model's capacity comes from. Here's the feed-forward, or FFN, formula inside a transformer block. At each token position, the model applies the same learned transformation independently. First, W1 and B1 expand the representation into a wider intermediate dimension. Then, a nonlinearity like ReLU or GELU is applied, and finally, W2 and B2 project it back to D model. In PyTorch, the key settings are D model, dim feed-forward, and the activation choice. This feed-forward block follows a narrow-wide-narrow pattern. We start at the model width, D model, expand up to a larger intermediate size, typically 4 times larger, apply the transformation there, and then project back down to the original width. In BERT, that intermediate filter size is set to 4H. More broadly, dense transformer LLMs often use expansion ratios in the 2 to 4 times range. Here's the key division of labor inside a transformer block. Attention is what lets tokens interact with each other. It mixes information across positions, so each token can pull in the context it needs from the rest of the sequence. Then, the feed-forward network works on each token independently, transforming that context-enriched representation. So, in short, attention handles communication across tokens, and the FFN handles learned feature transformation at each position. In the feed-forward network, the main things being trained are the two linear weight matrices, W1 and W2, which first expand the representation and then project it back down. The biases, B1 and B2, are trained as well, helping shift those activations. Through training, the model also learns useful nonlinear directions that strengthen task-relevant features and dampen irrelevant ones. All optimized end-to-end with gradient descent, usually for next token prediction. One key research finding is that feed-forward, or FFN, layers can be understood as key-value memories. They make up about 2/3 of a transformer's parameters. In this view, the keys align with patterns seen in training text, and the values help produce likely next token outputs. Lower layers tend to capture simpler surface-level patterns, while upper layers capture more semantic ones. So, attention routes information, and the FFN stores and applies learned pattern knowledge. You can think of the feed-forward network as a kind of learned memory. First, attention builds context by enriching each token with information from the surrounding sequence. Then, the FFN checks that representation against learned key-like patterns. When those patterns activate, their associated values help shape the output distribution. Finally, residual connections carry that information forward, so each layer incrementally refines the representation. One reason feed-forward networks are so expensive is memory. The intermediate activation tensor in the FFN can become very large. And in practice, it often makes up a major share of GPU memory, sometimes the biggest activation cost in a layer. The key point, though, is that FFN computation is position-wise. Each token is processed independently. That means the math for one token's FFN pass doesn't depend on any other token in the sequence. Here's a useful memory trade-off in the feed-forward network. In the standard FFN, you process the whole sequence at once, which is fast but uses more memory. With chunked FFN, you split the sequence positions into smaller chunks and process them separately. Since each position is independent in this layer, the result is mathematically the same after concatenation. The benefit is lower peak memory, exposed in hugging face as chunk size feed forward. At this level of engineering depth, the core challenge is training stability at extreme scale. DeepNet pushed transformers to around 1,000 layers, which means thousands of attention and feed-forward sublayers, and that makes gradient instability a serious issue. Their DeepNorm approach addresses this by modifying residual connections and adjusting initialization, so updates stay bounded. The result is stable training even as depth grows, including through the very parameter-heavy FFN layers. This slide is about the engineering choices that really shape transformer depth and performance. First, residual design matters. How gradients flow around the feed-forward sublayers has a big impact on how deep the model can train reliably. Second, normalization matters. Pre-norm versus post-norm affects both stability and quality, which is why PyTorch exposes this with norm first. And finally, activation choice matters too. GELU is the modern default, while ReLU and variants like SWIGLU remain strong options. To build a portfolio that really signals competence, focus on 3 projects. First, a minimal transformer lab, where you vary core settings like model width, feed-forward size, activation, and normalization. Then, track parameters, memory, and training behavior. Second, a chunked FFN profiler, comparing standard and chunked execution with real speed versus memory numbers. Third, a key-value memory probe, examining which inputs activate specific FFN neurons and what patterns emerge. Interviewers are usually testing 3 layers of understanding here. First, conceptual clarity. Can you explain the position-wise MLP that comes after attention, with expansion and projection? Second, training intuition. Do you understand that the FFN learns nonlinear transformations and can act like a kind of memory for pattern-conditioned responses? And third, engineering realism. Parameter cost, activation memory, chunking, normalization, and stability in deep models. Connecting all 3 is what makes a candidate sound senior. Here's a quick summary of the key FFN equations. The full feed-forward pass is W2 applied after a nonlinearity on W1 times X plus B1, then adding B2. In BERT-style models, the feed-forward dimension is typically 4 times the model width, for example, 768 expanding to 3072. The intermediate activations have shape batch by sequence by hidden expansion, and notably, the FFN often accounts for about 2/3 of total model parameters. Here's the career strategy in one test case, the feed-forward network. If you can clearly answer these 5 questions, you show the mix employers want: solid theory and practical judgment. What is it? A position-wise MLP with a narrow, wide, narrow shape. What gets trained? The weights, biases, and nonlinear feature transformations. Why is it expensive? Large intermediate activations. How is it interpretable? Like key-value memory. And how do you optimize it? Through chunking, normalization, order, and initialization. Here's the mental model to keep in mind. Attention is the routing system, mixing information across all token positions so each token gets context. The feed-forward network is the storage and response system, holding most of the model's parameters as learned pattern memories. It then transforms each token independently using that enriched representation. A Across layers, residual connections and normalization keep those updates stable, so the model can steadily refine its output. For AI engineers, LLM engineers, and agent-focused roles, the real differentiator is model literacy. It's not just knowing transformer terms, but being able to build, reason about, and improve models in practice. That means combining theory, architecture, formulas, and research framing with intuition about how components divide work and store information, and implementation skills like PyTorch, profiling, chunking, and maintaining training stability. Here are the key references behind this discussion. Vaswani and colleagues introduced the original transformer, pairing attention with feed-forward sublayers and residual connections. Divad et al. Later argued that feed-forward layers act like key-value memories, storing pattern-conditioned knowledge. Wang et al.'s DeepNet showed how to train extremely deep transformers stably using DeepNorm. And the Hugging Face documentation gives a practical method called feed-forward chunking to reduce activation memory during training.